Welcome to this proof of concept video. The goal today is to teach you to do modular arithmetic and do it easily, efficiently, and with intuition. No particular background is needed beyond the addition and multiplication we learn in grade school. Actually, you're already quite familiar with modular arithmetic because you understand how to tell time with a clock. The hours of the clock never exceed 12, and you might say that 11 plus 2 is 1, because 2 hours after 11 o'clock, it's 1 o'clock. That's just the integers modulo 12. So arithmetic modulo n naturally occurs in the universe. You've already met a bit of it when telling time, and our task today will be just to become familiar with it and able to do the computations. However, there's actually a lot more to reflect upon. Today's video is just a user's manual. How do you just do it in practice? The follow-up video will be a deeper dive into how and why it works, which is crucial to taking it further as an aspiring mathematician. We'll give a formal definition and prove that it behaves in certain ways, and we'll also expose some of the basic tenets of mathematical thought and practice. But for today, let's just learn how to do it, intuitively and efficiently. Okay, how do we work modulo n? We can do this for any n, so let's do an example with n equals 5. The number n is called the modulus. If we take n equals 5, that means we have a 5 clock. It has 5 notches around it, and we label them 0, 1, 2, 3, 4. Here's another example, n equals 7. This clock has 7 notches labeled 0, 1, 2, 3, 4, 5, 6. Let's go back to our 5 clock. In this universe, there are just 5 numbers, these 5 you see here. But we can still do addition and multiplication. Let's start with addition. Suppose you want to add 4 plus 3. Start with the notch labeled 4 and walk 3 notches further. The result is 2. So modulo 5, 4 plus 3 equals 2. Notice that when I write arithmetic facts modulo n, I do so with a 3-line symbol, equivalent or congruent, instead of the regular equal sign. I also write mod 5 afterwards because the modulus n, in our case 5, is so important here. Now let me just point out here that if we want to keep our sanity, this notion of addition had better be reliable in certain ways. So for example, if 4 plus 3 is 2, then we ought to have 3 plus 4 is 2. Let's try that. Start at 3 and walk 4 notches. We reach 2 again. Phew. Okay, that's it. That's addition on the clock. Multiplication is a little wackier, but at first pass, I could just take it to be repeated addition. So to compute 3 times 2, I could instead just compute 2 plus 2 plus 2. Let's try that. So start at 2, walk 2 notches, then 2 notches again. The result is 1. Of course, we could have interpreted 3 times 2 as 3 plus 3. So let's try that also. Start at 3, walk 3 notches. We arrive at 1 again. Great. Things are looking good. If you want to be able to compute modulo 5, that is, on the mod 5 clock, then we've done it. But this is likely to be a big hassle if you want to compute some large products. So let's revisit this clock from another perspective, which will make computations much faster. To see this perspective, let's go back to the integers. Let's draw the integers as a number line. The big idea here is to wrap the integers around the clock like rolling up a carpet. We do this so that the notches of the integers wrap up tidily over the notches of the clock. Now we identify all the integers over each clock notch as being the same, a sort of ray emanating out. So minus 5, 0, 5, 10, etc., these are all called 0. And minus 4, 1, 6, etc. are all called 1. For the name of each collection, I'm just using the simplest seeming number from the collection, the smallest non-negative one. You might observe now that we can characterize these collections by the remainder upon division modulo 5. So the numbers that lie over 0 are exactly those that are divisible by 5. The numbers that lie over 1 are exactly those that have a remainder of 1 when we divide by 5. And the numbers that lie over 2 are exactly those that have a remainder of 2 when we divide by 5. So this gives us a quick way to find the collection a number belongs to without having to draw the rolled up number line. So for example, what is 7 modulo 5? It has a remainder of 2 when divided by 5, so it belongs to the 2 on the clock. Take a moment now, pause the video, to tell me what is 77 modulo 5? That's right, it's 2, because that's the remainder when we divide by 5. In other words, taking away some number of 5s, we're left with 2. Okay, let me offer a quick interjection about notation modulo n. Instead of an equal sign, we use a 3-line symbol, which we read as equivalent or congruent. And we always have to remind the reader of the modulus since it will change what facts are true. And so Think of this mod 5 note here as sort of a margin note after the equation reminding us of the modulus. In particular, it's not part of the number. So we couldn't write something like this. The mod 5 is not part of the 77 or the 2. Instead, think of the 77 being congruent to 2 as the equation, and then the mod 5 notation here is just a little note off to the side after the equation is finished. Here's another way to think about these remainders. Within any one collection, any one ray, the differences are all multiples of 5. So for example, 6 and 1 are in the same collection, and their difference is 5. So you can move around on one of these arms or rays here by counting in 5s. We'll come back to this in the next video. All right, what about minus 1? Well, it has a remainder of 4, because we could add some 5s, just one of them in this case, to get up to 4. Now, if you're a programmer, here's an important note. The mod operation in some programming languages does the wrong thing to negative numbers. Please take a moment here, look at this picture that I've drawn, and convince yourself that minus 1 really should be 4 modulo 5 in a sane and organized universe. Okay, the moral of the story here is that every integer has a shadow on the mod 5 circle. Now, we have a great way to do arithmetic modulo n. We simply do it in the regular integers, then drop to the shadow on the clock whenever we please. So let's try 4 plus 3 again. In the regular integers, we get 7, then we drop to the shadow, which is 2. If we want to compute 3 times 2, we get 6, and drop to the shadow, which is 1. These are the same examples we computed last time, and we got the same answer, which is reassuring. But now, this is a much more efficient method than the first method. Let's suppose we wanted to compute 4 to the power 10 modulo 5. Using the first method, we'd have to break this down into repeated additions until we effectively wrapped around the clock 4 to the power 10 times and saw where we ended up. That is no good. But we can work like this now. 4 to the power 10, I could write that as 4 squared to the power 5. Square the 4, so we have 16 to the power 5. And now 16 can be dropped to 1 on the clock, so we actually have 1 to the power 5. And that's quick and easy. It's 1. So let's do another example, 17 cubed times 8. Pause the video here and give it a try yourself before you see how I do it. Okay, great. So here's how it worked for me. I did 17 cubed times 8 is actually the same as 2 cubed times 8 because 17 drops to 2 on the clock. 2 cubed is 8, so we have 8 times 8. And I can drop my 8s to 3s on the clock, so that's 3 times 3, which is 9, which drops to its shadow, 4. But perhaps you did it differently. But if you did it correctly, you will have gotten the same answer. Let's do one more. Let's pause the video now and compute 2 plus 9 times negative 3 cubed. Okay, great. Here's one way to do it. 2 plus 9 quantity times negative 3 quantity cubed is 11 times 2 cubed, where I've dropped the minus 3 to a 2. Now the 11 can be dropped to a 1, so that's actually 1 times 8, which is just 8, which drops to 3. So great. Now you can do modular arithmetic efficiently and with flair. Practice some examples, and you've got it. But wait. There's something bugging us here. Why does this even work? There are many different paths to the same answer. You can drop to the shadow at different points in the computation, and you should get the same answer. So for example, what if on the last one I did it differently? I did 2 plus 9 becomes 2 plus 4, and the minus 3 becomes 2. So we've got 2 plus 4 times 2 cubed. That's 6 times 8. And I can drop the 8 to a 3 and the 6 to a 1. So I've got 1 times 3, and that comes out to 3. I did get the same answer, but how do I know that that was going to happen? How do I really know that I'll get the same answer every time, no matter how I choose my path? I went about it in a totally different way, dropping different parts to the shadow at different times in the computation. That question leads us to part 2, the how and why. So watch the next video for an answer.